In the previous section, we did the best job we could in terms of defining abstract analysis functions. The purpose of this section is to check that we did not make any mistakes. The key idea of correctness is to ensure that whenever we have an execution sequence of the program graph, the memory that occurs at some program point has been properly recorded in the analysis assignment. We formalize this using the following definition and the following diagram, showing how the information in the analysis assignment properly records the semantics. To achieve this goal, it is useful to break it down into two subtasks that jointly will give us our assurances. The first is that the abstract analysis functions must somehow be sound with respect to the semantics. The other is that the analysis assignment solves some constraints arising from the analysis functions and the program graph. So let us make it clear what we mean by a specification of a program analysis. There must be a finite analysis domain, and for us it will be a power set of abstract memories. There must be monotonic analysis functions for each action alpha, and a set of initial abstract memories. We have not considered the concept of being a monotonic function before. It means that if we apply the function to a larger set, then also the result will be larger. Let us recall the detection of signs analysis that we have developed. Here are the abstract analysis functions for parsing a Boolean and for a symbol assignment. Now it is time for you to show that the analysis functions are indeed monotonic. We now approach our first subtask, defining what it means for a program analysis to be sound with respect to the semantics. This is illustrated by the diagrams shown here. Whenever a start memory sigma has its corresponding abstract memory contained in a set M, we require that the result of applying the analysis function to M must contain the abstract memory corresponding to the memory sigma prime arising from applying the semantics to sigma. This can be expressed by the following conditions. That also takes care of the initial memories. It is proved in the book that the semantic analysis functions defined in the previous section are indeed sound. One lemma used is that the analysis of arithmetic expressions is correct. Another is that the analysis of Boolean expressions is correct. We now approach our second subtask, that of ensuring that an analysis assignment solves the constraints from the program graph. This is illustrated by the diagram here. Whenever we have an edge, the analysis information at the target node must contain the result of applying the analysis function to the analysis information at the source node. This can be expressed as done here, also taking care of recording the initial memories at the initial node. For the factorial program, this amounts to checking the following constraints that we informally talked about also earlier. It is time to summarize the results. What we want to obtain is that the analysis assignment is correct, and the diagram shows the way we have defined this. It is achieved by the following two subtasks. First, to ensure that the analysis specification is indeed sound with respect to the semantics. Next, to ensure that the analysis assignment actually solves the constraints specified by the program graph. We can summarize this insight by means of a short proposition. Now it is time for you to read the text in the book, doing the try-it outs on the way.